So we're talking about Kalman filters, but we're going to start with something called recursive filters. And the first one isn't going to seem much like a filter. It's a recursive expression for the average. So just taking an average of some data points. So a recursive expression or the average. Recursive just means it's changing in time. It's changing as you march forward along a data set. So first, let's just assume that we've got k data points. And these could be, we'll think of these as scalars for now, but later they could be vectors. So we've got x1 is the first measurement, x2 the second, so on, all the way to xk. We've got k data points. So then x bar k is going to be the average over these k data points. So what is it? It's the sum x1 plus x2 all the way to xk divided by the number of points. This isn't anything you don't know. This is just an expression for the average. But it does take in all k points. So we'll call this a batch expression, which is different from a recursion expression, meaning it takes the whole batch of points. So if k is large, let's say greater than 1,000,000 or something, then this could be computationally expensive. Because let's say now we get 1,000,000 plus 1. Now you got to add all 1,000,000 plus 1. And we don't want to do that. We want to do something that could be quick on the fly, something that's especially very quick to compute for something on board a vehicle or any kind of craft or some kind of small CubeSat. These things don't have the computational power of the cloud or the ARC supercomputer or even sometimes our iPhone. If you've used Arduinos and things, they've got little microprocessors, and you want to try to make the algorithm as simple as possible so that things can work in real time. So we are going to be concerned about how computationally expensive is this. Adding up 1,000,000 things and then adding up 1,000,001 just doesn't really cut it for us. So we want to write a recursive expression, meaning we want to write x bar k, the average over k, in terms of the average, the previous average, x bar k minus 1 plus something new. What is x bar k minus 1? This is just the sum over all of these up to xk minus 1, and then divide by the total number of points here, xk minus 1. Okay, so far so good. Now we'll write, going back to this expression up here, if we multiply both sides by k, we'll have k x bar k equals, and then what is it? x1 plus x2 plus dot 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 plus xk minus 1 plus xk. Well, we could write this in a similar way. We could write it as k minus 1 times x bar k minus 1. And now what? Now let's divide both sides by k minus 1. And we'll get k over k minus 1 x bar k equals x bar k minus 1 plus xk. I'm going to put this in another form by, I want to have x bar k by itself. So we're going to multiply both sides by k minus 1 over k. And what do we get? X bar k. Oh, I think I forgot to put this. This has a k minus 1 over it. So there we go. X bar k equals k minus 1 divided by k. So some factor in front of x bar k minus 1 plus 1 over k xk. So this is the recursive expression. meaning it takes in the previous estimate that you could store the new data point, and then it spits out now the new estimate of the average. So that's what makes it recursive. Gives X bar K from the previous average, X bar K minus 1, and the new data point, XK, and the number of data points. Okay. At least number of data points so far. All right. So this is faster and more efficient. So we'll do a really simple example. Suppose our data is 10, 20, and 30. Well, we can pretty easily calculate what the average is. X bar. There are 3 data points. And so 10 plus 20 plus 30 divided by 3 equals 20. That would be the batch computation. But suppose we did this sequentially. So if we started with K equals 1, then from this expression up here, X bar 1 equals, well, we've got 1 minus 1 over 1, so that's 0. And X bar 0 is not even defined, so that's good. Let's multiply by 0 plus 1 over 1 times X1. X1 is this first thing. So we get 10. So if we're marching through the data, our first guess of the average would be the guess is 10. About X bar 2. This is K minus 1 over K is now 1 over 2, that previous estimate of the average, plus 1 over 2, the new data point. So this is 1/2 of 10 plus 1/2 of 20. So this is 15. It's getting closer to the true average. K equals 3. Well, we expect it to be the same, but written in the recursive form, X bar 3 equals, so now K equals 3. K minus 1 over K is 2/3 the previous estimate, plus now 1 over K, 1/3, the new data point. And so this is going to be 2/3 of 15 plus 1/3 of 30. 20. So, hey, what do you know? The same thing. Good. It's just that if you're doing this on the fly, you'd want to use the recursive approach. If inside your computational sensor thing, it's a lot easier for it to do this marching along recursive approach. All right. We're going to write that K minus 1 over K factor in a different way. Let's define alpha. This alpha is K minus 1 over K, which is also 1 minus 1 over K. Therefore, 1 over K is 1 minus alpha. So the recursive expression for the average is, we could write it this way, X bar K equals alpha times the previous average, X bar K minus 1, plus 1 minus alpha XK, where alpha is K minus 1 over K. This thing is called the average filter. All right. And alpha is tied to the number of data points averaged. Later, we're going to see an expression that looks just like this, but it's not related to the number of data points. So alpha will be free. Here, alpha is not free. And we're going to apply this. Let's apply this to an example. So where this is important is when you're trying to measure something that's noisy. And anytime you have measurements and sensors, there's going to be noise. So let's do an example of measuring voltage, where the voltage should be 14.4 volts, but we're going to add noise. And the noise will be uniformly between -4 and 4 volts. We could code that in MATLAB using the random number generator. So this is what we're going to do. You could either think of this as time down here or K. K is sort of like the discrete version of time. And if the measurement is really wild, well, it has noise. So I don't know what it's going to do. I'm just sort of putting data points and then some kind of dashed line between them. If we were to calculate what the true average is from all data points, we would get this. If we use something like the recursive filter, we'll probably get something that will slowly converge to the true. So green is the recursive approach, which is that average filter. And red is the batch approach, right? So let's try this now. Go into MATLAB, but there's this MATLAB demo of recursive filters. And so I'm giving you all the code that I'm going to show you today. So you can go through all of this if you want. We're talking about the average filter. Let me show you the average filter. So this is the average filter function, and I'm using this thing called persistent. So in MATLAB, if you define a persistent variable within a function, it means that anytime you call that function, it'll remember that variable. It's sort of like a local global variable. So what this does is the first time this is run, it initializes, it says the previous average is 0 and that K equals 1. And then beyond that, it doesn't call this part again. It writes what alpha is, and alpha is tied to the number of data points, which is K. And then here's computing the average. Average is alpha times the previous average plus 1 minus alpha times the new data point. So that's what this takes in, the new data point, and it marches forward. And then it says the previous average is this calculated average, and K now increases by 1. Okay, get volt, it spits out Z, which is the voltage. So the voltage, I'm saying on average should be 14.4, plus we're adding a noise term, W. And the way we've written W is it has an average of 0, plus it's 4 times this rand n, it just gives a random number. Rand n gives a random scalar between -1 and 1. So we're just multiplying it by 4. So this goes between -4 and 4. So that's the sort of the range of the noise we'll get for this. And we're hoping that our recursive filter quickly finds 14.4. So if I do test average filter, I'm saying that the voltage, just to sort of set it up for later things that are connected to time, that the time step between each measurement is 0.2 seconds. And I'm going from 0 to 10 seconds. So however many samples that is, I guess it's 50. And this will just march through and it'll plot the true voltage and then what we're getting for our recursively computed average. So let me run this. I need to go to that folder. And I like to be able to see things and put a grid on it. There we go. So here, the dashed lines with stars, that's this voltage measurement. It's a fake measurement. It's 14.4 plus this noisy term. And the dashed line is the recursive average. And we're seeing that it's the last value, it's around 13.8. So it's actually getting close. As time goes to very, very long, it should get arbitrarily close to 14.4 because this noise is evenly distributed about 14.4. So this is how you would compute a moving average. And where might you use this? This would be if you were to, this gets used a lot when you're calibrating something, when you initially turn it on. You turn it on, and as long as there's no motion or nothing to sense, this thing will settle down to some kind of baseline. In this case, we've set the baseline as 14.4 volts. So in this case, we had something that was actually, it was noisy, but around something that's constant. But what if you have something that's changing in time? So I'll give an example of a measurement where we're looking at the altitude based on a sonar measurement, and it's going to look all messy. So if you're doing a test of like the altitude for an aircraft or a rocket, and you're using some kind of noisy measurement, you don't want to take the full average. The full average for this might be something like that, and who cares? What you want is something that can kind of smooth out these jagged things, because maybe you want to eventually take that altitude and calculate a derivative to get like the vertical velocity. And you can't do that when you have something so jagged. So to be able to get something where a signal is changing, if signal is changing, then you want to use a moving average. Meaning it's not averaging over everything, it's sort of averaging over the last n data points. And you could change that window n to get different things. So I'll call this the moving average filter. So what do we want to compute here? We want to take k minus n plus 1 setup. K minus n plus 1 plus, then the next one, plus x k minus n plus 2, all the way up to xk. And these are, this is n data points. So if we want an average of that, we divide by n. Now we're going to call this x bar k, but it's different here than it was before. It's different than before. This is at the kth data point. We've computed the average of the last n data points. Or the previous n data points. That's what we call it. It's a moving window, n points, and we're just averaging them. So we don't care about what came before or after. Now, we want to write this in a recursive way. And I could go through similar steps that I did before to get it. I'm just going to give you the result. Written recursively. the moving average at the kth data point is the same as the moving average at the previous data point, the k minus 1th data point, plus some new stuff. The only new stuff is xk minus xk minus n divided by n. And you might wonder, well, what about the other? It seems like there's a lot of data points missing in here. Well, they're all sort of embedded in this expression. So this is writing things recursively. So it'll give some speed up, because instead of having to average n points, we're just kind of taking 2 points, xk and xk minus n, dividing by n. So this will be quicker than a batch thing. All right. So this is the moving average filter. And what are the things we have to pick? We pick n. So let's apply it to some example data. It's actually sonar altitude data, which is noisy. Nice thing about MATLAB is the stuff is easy to code up. So MATLAB again. So let me go back. There's this thing called the moving average filter. Let me just show you what that looks like. The average filter too. I don't like that. Let's get rid of that. So here I've hard coded in when the first run happens. N equals 10. So I'm choosing 10. I guess I should show you what it looks like, so you know what the sonar alt. I forget what this is called. Sonar. Did I clear all? There we go. Okay, plot that thing. So that's it. It's make the fonts bigger. So this is showing altitude. You can see it goes from like 30 to 120 here. And then this isn't time. This is just sort of data. So it depends on, if we wanted to get things like velocity, we'd have to know what the actual time step is here. I think it's like 0.2 seconds, but I have it in the code somewhere. This is just showing you, this is the signal that we're going to try to apply a moving average to, because we don't actually believe that the altitude really went up by a few meters in 0.2 seconds and then went down. We think this is probably due to the noisiness of the sensor, because that's life. So let's close that and see what the so the moving average filter, this is just a way of coding up what it does. And now what? Let's test this. I want to do the first 500. Oh, I think I want to do all of them. All right. Yeah. Okay, so down here, this is saying that the time step between them is actually 0.02 seconds. Okay. And then we'll get a measured and a moving average. And I want to do location. This just sort of determines where the legend goes. What if I do this? Run. Scared. Okay, there it is. Make it visible. Add a grid. So this is showing in red the actual measurements. And based on a moving average of 10, you could see that we're sort of picking up things, but we're getting rid of the extreme parts. So if I just sort of focused on the first, say, 10 seconds, It seems to be following the trend well, but there does seem to be this problem that our moving average is sort of delayed when there's these ups and downs. You can see that it's kind of delayed. When things are kind of steady, it's hard to tell, but when there's these definite shifts, it's delayed. And that delayed increases as we increase n. So n sort of represents a trade-off. The larger the n, the smoother the curve you'll get, but the larger this delay will be. And maybe you don't want a large delay. I can plot, let me try this with, I'll do an n of 100. And then I'll do the moving average as a thicker black line. There we go. And run. So increasing n, you could see it does make it smoother, but we're missing probably some signal here that's important. Like I believe that this thing kind of went up and down. This is probably from a drone or some kind of aircraft that does drone-like things. But this delay is even longer. So there seems to be a problem with this moving average that we'd like to fix. So there's an improvement upon the moving average, and it's called a low pass filter, which maybe you've seen before. The idea here is it allows low frequencies, which we think of as the actual signal we want, and filters out high frequencies. And why are we doing that? The assumption is noise is going to be high frequency. It's going to be random and make those kind of spiky things. So how do we do that? And why are we doing this? Because we're doing this because there's limitations to the moving average. And we can see that if we were to write out the expression for it, xk, so I'm just rewriting what I had. This is xk minus n plus 1 plus xk minus n plus 2 all the way to xk, all divided by n. I'm going to write it out in a way that sort of makes more apparent what the problem is. We have this factor of 1 over n in front of all of the terms. So the same factor, each term has the same weighting, 1 over n. So even the most recent to the one that's the least recent. And so I want to ask you, if you're tracking either an aircraft or a spacecraft that's maybe doing some kind of aggressive thing, and maybe it's taking 1,000 measurements per second, do you think the state at the end of that 1 second is closer to the final, the most recent data point, or the one that's 1,000 data points ago? Yes, the most recent one, yeah. But that isn't what this does. This weights them all equally. So we probably, if we want to get rid of this problem of weighting everything equally, and this is probably related to why we see the signal seem to shift and be delayed, is because we aren't weighting things properly. So what we want to do is weight the more recent data higher than previous data. In terms of something like a moving average, but we're calling it something else. We want to weight more recent data higher than older data. So the thing that addresses that is a low pass filter. If you take a course in signal processing, you'll probably hear a lot more about this. I'm just giving you kind of the basics to get to the Kalman filter. So there's a first order low pass filter. And this is the expression. X bar K is alpha X bar K minus 1 plus 1 minus alpha XK. And this should look familiar. This is exactly what we wrote for the expression for average, but there alpha was related to the total number of points. Here, alpha is a free variable. So alpha can be anything less than 1 and greater than 0. So this is a first order low pass filter. And we will be able to see what alpha does. So this looks like expression for the average. Not the moving average, just the average. But here, alpha is a free parameter that we get to pick. And if you think about it, when before, when we're looking at the average, alpha was defined to be K minus 1 over K, which if K is large, this is going to 1. But now we don't have to go to 1. We could do 0.7, 0.5, 0.3, and it'll affect things. But this is what we're calling a first order low pass filter. We're also not going to call X bar K an average. We're going to use a different term. It gets to what we're really interested in. From now on, X bar K won't be called the average. We'll call it the estimate, because in some sense, that's what it is. It's trying to take noisy data, and as you're going along, try to give you the best estimate of what the true value is. And in a more elaborate way, that's what the Kalman filter does. It's taking in measurements and trying to give you a best estimate of some desired state. All right. So we're going to call X bar K an estimate. So in this thing, this is saying the estimate at the kth time step is equal to alpha times the estimate at the K minus 1 plus something new. Now, does this really overcome the problems with the moving average? That's why I even put this in here. And that the main problem was that it was weighting all of the data points in the window equally. We don't want that. So let's see if this does solve that problem. We will start with writing what this expression would be for X bar K minus 1. So just following this up here, X bar K minus 1 equals alpha X bar K minus 2 plus 1 minus alpha X K minus 1, the X K minus 1 data point. Now we'll sub this into the expression up here. X bar K equals alpha X bar K minus 1, but I'll just substitute in this whole thing. Alpha X bar K minus 2 plus 1 minus alpha xk minus 1 plus 1 minus alpha xk. And just expand things out here. Alpha squared x bar k minus 2 plus alpha 1 minus alpha xk minus 1 plus 1 minus alpha xk. So what does this show us? It shows us that the most recent data point is weighted the highest because we've got alpha minus 1. This also has alpha minus 1, but it's pre-multiplied by alpha, which is less than 1. So that means this weighting is going down for the data point that was just 1 unit ago. And this will keep on going. If we were to expand this out, you'd see that all previous data points are being weighted exponentially smaller related to this factor alpha. So this alpha, 1 minus alpha, is less than 1 minus alpha. Hopefully that's clear, since alpha is less than 1. So previous data gets weighted exponentially less. So it seems like it is solving that problem. We're going to have something that seems like a moving average, but it's weighting the more recent data points higher. So let's just do another MATLAB demo. Same sonar altitude data. I'm now going to this thing that says number 3, low pass filter. See what the low pass filter looks like. So the low pass filter, it's a lot like the average, except now alpha is a free parameter. So we can put in any alpha we want. It's not tied to the number of data points. So very similarly, LPF here means low pass filter. It's alpha times the previous estimate plus 1 minus alpha of the new data point. And then we save in the previous X as this, and it just kind of goes from there. So we will, if I do test the low pass filter, I'm going to take in, I think there's 1,500 data points total here. I could start with any alpha I want. We'll try different alphas and just so you could see. So if I try it very close to, if I try super duper close, 0.999. So let's see what this bad boy does. Change folder. Ooh, check it out. Oh. Okay, so this is the low pass filter. If you do 0.99, and it's terrible. It's just miserable. I'm going to do that again just to see. I think it'll do the whole range. Yeah. Great job there. I mean, what it's trying to do is get the average of all of the measurements, right? As alpha goes to 1. So this isn't very good. Let's try something else. Let's try alpha of maybe 0.7 and see what that does. Okay, so now it's showing both of them, showing the terrible, terrible alpha of 0.999. And now look at what 0.7 does. It seems to be tracking pretty well. It doesn't even have that problem of a delay. So that's pretty cool. Seems like there's a little bit of a delay. So this term alpha, it's kind of tuning how much do you weight all of the previous points. As it gets closer to 1, it's weighting all of the previous points more. As alpha gets closer to 0, it's weighting all the previous points less. So this is just 0.7, and it's giving something pretty good without much of a delay. If we want, we try 0.3 and just see. I think it'll overlay top of here again. So that is more jagged. You can't really see. It's the more jaggedy one, which jaggedy isn't good if you're going to do something like take a derivative of this to get a velocity. So a low pass filter is a way to get a smoother curve. And what's its point? The point is to try to get a best estimate of the true state. But it's not very smart. The Kalman filter comes in and makes this smarter. And how does it do that? A Kalman filter is basically a low pass filter where alpha changes for each step. And this alpha gets changed according to some formulas that when you first see it, you go, oh my gosh, that's intimidating. But it doesn't need to be. Is there anything else you have questions about this? You could play with this data and do whatever. You could use it on your own data. We haven't yet got to the hardcore stuff. All right, all of this this is just preliminary stuff. It's good to know, but it's preliminary to the Kalman filter because we'll see a lot of commonalities. Of course, we're not going to get to it in like 15 minutes, but I will show you an outline of the Kalman filter. I don't really know the history. I think the guy's name was Rudolf Kalman. And at some point, it got noticed by the aerospace community in the late 60s, when, according to some people, civilization reached its peak, and we've been going down since then. Sorry. I mean, I was born after that too, so that's overly dramatic. I don't think we've passed our peak. But because of the Apollo program and things, there was a lot of interest, and really aerospace is the main user of the Kalman filter. Now, let me just sort of repeat something I think I said in passing. It's like a low pass filter. Remember why low pass? To filter out high frequency noise. It's like a low pass filter with a dynamically changing alpha. So instead of picking an alpha once and for all, it'll change it in some recursive way. So there'll be something like alpha K, but really. Another thing you need to know, some people think they got to know the theory. Nobody here, I hope. You can apply the Kalman filter to real world data without a heavy theoretical background. I mean, just like we use ODE solvers, and I don't know how they work. Well, maybe I do, but to commiserate with you, I don't know. It's a black box. You can apply the Kalman filter to real world data without the heavy burdensome theoretical background. So let me just give you the Kalman filter algorithm, and we'll just sort of break it down. For many of you, it'll be immediately useful. If you're doing anything with gyroscopes and stuff, and you want to estimate the rotation, or really anything, be good to know. So this might be hard to see, but there's some kind of loop structure to this. Where does it start? In some sense, you're taking in measurements, and this, in the language of Kalman filters, it's usually called Z, and this is saying Z sub K. So at the say K, at time K, you take in a measurement, it does something, and it spits out an estimate, the best estimate of a state. The nice thing here is that measurements and states could be different. Bless you. Measurements and states can be different. For example, ZK could be the sonar data, which is supposed to be altitude, but it's kind of noisy. And XK, and the hat thing means it's the estimate. XK could be the altitude and the velocity. So even though, technically we aren't measuring the velocity, we can estimate it because we know how position is related to velocity. It's related to, change in altitude divided by the time step. So if you have measurements that are equally spaced in time, and they don't have to be equally spaced in time, but if they were, that makes it simplest. There's two different major steps. There is a prediction step, and this is what we'll get into more next time. So there's a prediction step, and it might be hard to see what those things are. We've got what it calls X, K, hat, and the hat thing is just part of Kalman filter notation. And then this minus sign. This minus sign is important because the minus means it's like before you do the estimate. Minus means a prediction. So the Kalman filter does something where it tries to predict what the next step will be using a simplified linear model compared to the previous step. And we'll say more about this next time. There's also, so this is the predicted state. There's also this thing PK. This is called the error covariance, and it's often a matrix. And so PK minus, this is the predicted error covariance. It's a measure of noise, and this thing changes. So this is kind of related to what alpha will do. The next step is called an estimation step. Something gets computed using a bunch of matrices, and it looks confusing, but it's not. We can talk about what those things are. There's an estimation step, so you compute this thing called the Kalman gain, which is, I guess, is more related to alpha. And then that goes into this estimate step, where you take in the measurement. Kalman filter gives the best estimate it can for the state. And then after that, it computes the error covariance, and things go back to the top and repeat at the next time step. So there's the two main steps, prediction, estimate, and I think we'll leave those for next time. We're not done yet. Let me give you kind of a summary of what these different terms are. The external input, this is a measurement from a sensor, and measurements are expected to be noisy. The estimate is the estimate of the thing you want. The system model, this is where you have to actually think about what's specific to your physical situation. And I say that because, in this class, we're focusing on physics, but you could apply this to anything, like tweets about Cardi B or something. I don't know. And then there's these other things that are just computed internally, and you don't really have to worry about them. A is a matrix that's related to your best estimate of a linear model for the process going on. H is just related to picking how the measurements will map to the states. And then Q and R are related to noise levels. So sometimes with sensors, you're told ahead of time, here's the noise level. Otherwise, you'll have to pick the entries of Q and R. It's just a diagonal matrix. You pick the entries and you can tweak them to tune your Kalman filter. So Kalman filters need some tuning to get the right answer. If you aren't told ahead of time, this sensor has this error, like it's known. Usually when you get something, like I use wind sensors all the time, and often it'll say, above 2 meters per second, the error is 5% in the wind speed. So, okay, that gives me some idea of the error. So we'll go into more detail next time.
If you appreciated this video, please like and subscribe, or just wait and watch the next video in the series. There are links and other materials in the description.